Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 2.8, Rates of Change and Differentiability.
Lesson 1, Rates of Change.
Well, the next thing we're going to do is to try to extend our ideas that we've been talking about in these last few pages. We've been talking about instantaneous velocity, which is really a rate that your distance is changing with respect to the input variable of time. And what we'd like to do is extend that to other types of quantities besides just distance and how they can change in time. And in fact, we'll even talk about different types of input variables. Instead of thinking of distance as changing in time, it could be distance changing with respect to some completely different type of input variable. So we're going to be expanding and generalizing on these ideas of one quantity changing with respect to another. So let's go ahead and look at the next slide and see how that would work. So this little section is called rates of change. We've been discussing the rate that distance changes in time. So let's go ahead and just remember that s was our position, or you could think of it as the distance function, and t was the time. The average velocity was the slope of the secant line to our curve, and it was the average rate of change of the distance with respect to time. And in a similar way, the instantaneous velocity was also the slope of a line, but it was the slope of the tangent line, and it was just the instantaneous rate of change of distance with respect to time. So now, instead of thinking about a specific application of distance and time where s is equal to f of t, let's think about a more general function where we have any output quantity y equals some function of any input variable x. And what we're going to do is extend these ideas of average velocity and instantaneous velocity to this more general case. So in general, for any such function y equal f of x, we are going to define the average rate of change of y, our output variable, with respect to x, our input variable, as the slope of the secant line to the graph of y equal f of x. And the instantaneous rate of change of y with respect to x we will define as the slope of the tangent line to the graph of y equal f of x at the value x. Well, how would I calculate these things? Let's go back and remember how we calculated the average velocity and instantaneous velocity, and we'll extend those ideas down here. Remember that the average velocity was the slope of the secant line, and we calculated that by finding the change in s, the distance or position function, as compared to the change in t. And we simply calculated the change in the output values s and divided by the change in the input values t. So we're going to do exactly the same thing for this general function. The slope of the secant line is just the change in the output values. Well, the outputs are now y's, and I'll divide by the change in the input values. Instead of t, the input values are now x. So the slope of the secant line can be found by doing delta y over delta x, and that's also how we can find what we are now calling the average rate of change of y with respect to x. To find the instantaneous rate of change, it's just the slope of the tangent line. And remember, for instantaneous velocity, the way that we found it was to find the slope of the tangent line on this curve, s equals f of t. How did we find the slope of the tangent line to that curve at a particular value t? We just found the derivative, f prime of t. We're going to do the same thing down here in the general case. To find the slope of the tangent line to this curve, y equal f of x, at a particular x value, we simply find the derivative of this curve. So the instantaneous rate of change of y with respect to x can be found by just finding the derivative and evaluating it at whatever value of x we want to find the instantaneous rate of change at. And the average rate of change of y with respect to x can be found simply by finding the change in the y values over the change in the x values as x goes from one value to another. In terms of the graph down here, the average rate of change of y with respect to x, we said is the slope of the secant line. Here I have the black graph as y equal f of x, and here's the secant line through 2 points going from one x value to another x value, and the slope of the secant line we said we'll figure out just by doing the difference in the y values over the difference in the x values. If I want the instantaneous rate that y is changing with respect to x, so I'll call that the instantaneous rate of change of y with respect to x, we said you find the slope of the tangent line. If this is my black curve, y equal f of x, and I want the slope of the tangent line at any particular point x, I just go ahead and find the derivative of my function and evaluate that at x. Okay, so in the next couple of examples, we'll be looking at rates of change that are rates of change of functions other than distance with respect to time. And in our very last example, we'll even look at a rate of change of something other than distance with respect to an input variable other than time. We're going to look first at a couple of examples. Okay, so the first example we're going to look at is an example where your weight is described in terms of your age. So we're going to have weight on the vertical axis and your age in years on the time axis. And it's described with a graph, w equals f of t, so we don't know specifically what function of t w is equal to. We're not given the equation, but we are given the graph. And we're going to try to answer some questions about how fast your weight is changing over your lifetime. So let's just look at this picture for a moment of this graph. Here you are at 0 years old at birth, and you weigh some amount, maybe 10 pounds, something like that. And as time goes on, your weight increases. So here you are at 10 years old, 20, 30, 40, 50, and this graph only goes up to 60 years old, but presumably we could extend it beyond 60 years old. Let's see if we can answer some questions here. In part A, we are asked to approximate the slope of the tangent line at the point P. And you notice that the point P is at the time that you are 10 years old. Say it's your 10th birthday, the instant when you turn 10. So let's try to approximate the slope of the tangent line there, and the tangent line is actually drawn in for us. And then we'll try to interpret what that slope means. So let's go ahead and start by just seeing if we can figure out what the slope of the tangent line is when you are 10 years old. Well, like the slope of any line, we can find the slope of the tangent line by looking at the rise over the run of that line. And so I'm looking at this purple line, and to find its slope, I want to figure out its rise versus its run. I'm going to try to pick out 2 points along this line that fall on grid points. It will just make it a little bit easier to figure out the rise and the run. So I could pick any 2 points along the purple line, but why don't I choose this one, because I see that it crosses at a grid point, and this one, I can see that it also crosses at a grid point. So I'm going to try to figure out what the run is and what the rise is between those 2 points on my purple tangent line. Well, it looks to me as if the rise, well, I'm going from a weight of 0 pounds up to a weight of 100 pounds, so the change in weight, or my rise, would be 100, and we can put pounds on there for units. And for my run, it looks like this point is halfway between 0 and 10, so that would be age 5, and it ends at age 20, so that would be a run of 20 minus 5 would be 15 years. So that's the change in time. So the rise here would be 100 on the pound scale, and the run of my purple tangent line is 15 years on the time scale. If you want to plug that into a calculator, that's approximately 6.7 pounds per year. So that is the slope of the purple tangent line. Now we're asked to interpret this. And what does that mean, the slope of the tangent line? Well, we just got through saying on the previous page that the slope of the tangent line is the same as the instantaneous rate that your, I'll say, rate of change of your output variable. Well, what's our output variable? Our output variable is W, so it's the instantaneous rate of change of W, which represents our weight, with respect to our input variable, which is t in this case, or time. So this 6.7 pounds per year is the instantaneous rate your weight is changing compared to your age at the moment that you turn 10 years old. So it's how fast your weight is changing at the instant that you turn 10. So you wake up on your 10th birthday and it's saying that you are gaining weight at approximately 6.7 pounds per year at the moment that you turn 10 years old on your 10th birthday. So another way to say this is when you turn 10, at that instant in time on your 10th birthday, you're gaining weight at the rate 6.7 pounds per year. Okay, let's go ahead and look at part B. Maybe you can think about it a moment yourself. We are going to be asking, when are you gaining weight the fastest? And remember that the rate that you're gaining weight, the instantaneous rate of weight gain, is the same thing as the slope of the tangent line to our black curve that represents W equals f of t. So pause the video for a moment and try to answer this question. Try to pick out the age at which you are gaining weight the very fastest. And then restart the video and we will go through it together. Well, we said the instantaneous rate of weight gain, the instantaneous rate of change of W with respect to t, is the slope of the tangent line. So when I ask, when are you gaining weight the fastest, I'm really asking, when is the slope of the tangent line the largest? So if you consider different tangent lines to this graph at different points, different ages t, you can ask yourself, when is the slope of the tangent line the largest? In other words, when is the tangent line the steepest? So what we're really doing is looking for, I'll put in parentheses, we want to look for the point at which you have the steepest tangent line. Well, let's think about it. When you're born over here, there will be a certain, draw it in red, there'll be a certain tangent line to the curve, and the slope of that tangent line represents how fast you're gaining weight on the day of your birth. When you get to be 5 years old, there's going to be a different tangent line, and you notice that it looks like the slope of the tangent line at age 5 is a little bit larger, so you're gaining weight faster at age 5 than you were when you were 0 years old. Here was the purple line that was the tangent line to the curve when you were 10, and we found that the slope of that turned out to be 6.7. When you get to be 15, you have another tangent line to the curve, and that one looks pretty darn steep to me. That looks fairly steep. Beyond age 15, it looks to me as if the tangent line slopes start to flatten out a little bit. So to me, it looks as if the very steepest tangent line would occur right at age 15. And so, at least as accurately as we can get from a rough graph like this, I would say that when are you gaining the weight the fastest? It's the moment that you turn 15 years old. Okay, let's look at part C of this problem. What happens to the rate you're gaining weight after this age? In other words, when you are greater than 15 years old. So again, try to think about this yourself, pause the tape, and then we'll come back and try to answer it together. Okay, so what happens to the rate you're gaining weight after this age? Well, we said at 15 years old is the very steepest tangent line. What happens to the tangent lines after that? They look less steep. They still have a positive slope, so your weight is still going up as your age increases. But it looks like the rate that your weight is going up is getting smaller. So one way of answering this question would be to say that after 15, the slopes of the tangent lines are positive but getting smaller. So the tangent lines are sort of flattening out as we get older. So the slopes of the tangent lines are positive but getting to be smaller and smaller values. And remember that the slope of the tangent line is the instantaneous rate you're gaining weight. So what does that mean? It means the rate you're gaining weight is getting smaller. You're still gaining weight, but less and less weight per year as time goes on. One last thing I want us to consider before we leave this example is what would happen if I extended this graph past the age of 60 years. Suppose that I extended it in a way that the black curve started to come down. So maybe if you're 70 years old, just extending this graph a little bit, maybe your weight starts to actually drop. Maybe you have some kind of post-midlife crisis. You decide, I'm close to 200 pounds, I don't want to be that heavy, and you start on a running program or some kind of exercise program, and your weight actually starts to go down. Well, if we thought about the slope of the tangent line at such a point, like at the point where your age t is equal to 70 years old, let's think about what happens at that point. If I draw the tangent line there, you notice that it is a straight line that is falling as I move to the right. And what does that mean about the sign of this tangent line? Well, it means that if you look at the rise and the run on this line, you'll have some certain positive run as your age increases, but the rise is really a negative number. So the rise is really a negative value for the change in your weight. So just notice that a line that is moving down as you move to the right is going to have something that has a negative slope. Maybe the slope turns out to be negative 1.5 or something like that. So if the slope of this red line is negative 1.5, I'm going to add units to that, negative 1.5 pounds per year. How would we interpret that? What we're really saying is that as you grow 1 year older, so as your age increases by 1 year, perhaps your weight is going down by 1.5 pounds. So if your weight starts to decrease, that's going to be reflected in the fact that the instantaneous rate your weight is changing is a negative value. It's a negative slope to our tangent line. Okay, well, let's go ahead and look at one last graph function. We're now going to consider your weight not as a function of time as we did here, which may be a little bit more straightforward to think about, but we're going to think of your weight as a function of your height. That sounds kind of weird. W is equal to some function of h. But if you think about it, it sort of makes sense. Think about when you were very short, like the day you were born, perhaps you were only 1 foot tall and you weighed 10 pounds. And so this is going to be a point that represents the start of your life where you're at a height of 1 foot and you weigh 10 pounds. Well, what happens as your life proceeds, you start to get taller. So you grow to be 2 feet tall, 3 feet tall, 4 feet tall, 5 feet tall, 6 feet tall, and so on. And what happens to your weight? Well, generally as people get taller, they also gain weight. So your weight is going to go up. And so you notice that this is generally I guess this is always an increasing graph in this case, although you could actually lose weight even though you gain height. But for this particular person, it looks like their weight continues to go sort of upwards, upwards, upwards as they gain height. And this graph is ending here at 6 feet tall, probably because the person grew to be 6 feet tall and then they didn't grow any taller than that. So this particular curve has definite endpoints with the starting point at whatever height the person was when they were born and the end point corresponding to the height they were when they stopped growing. Well, we're going to do the same kind of thing that we did up in part A of the previous example. We're going to approximate the slope of the tangent line at the point P. That's at the moment in time when your height is 3 feet tall. So you start out at 1 foot tall, you start growing, 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 growing. At some instant in your life, you're exactly 3 feet tall, and we're going to approximate the slope of the tangent line to our black W equals F of H curve right at this point P. So the tangent line is actually already drawn in for us in purple. And to figure out the slope of that tangent line, again, all we want to do is figure out what the rise over the run is of that purple line. And if the line weren't drawn for you, you could sort of eyeball it, but it's been drawn for us. To find the rise and the run on this purple tangent line, again, it's easiest to find points that appear to be grid points. And it looks like this point P is actually right on a grid, so I'm going to use that point. And it looks like this point right here crosses a grid, so I'll choose those 2 points. They're just more convenient than if I choose points that don't cross my graph at a grid point. I want to figure out the rise of this line. Well, it looks like as I go from here to here vertically, I'm going from 50 to 100, so the rise is 50 along the pound scale. And the run, I'm going from here to here, so the run is going from 3 feet tall to 5 feet tall. It looks like that is a change of 2 feet. So the slope of this purple tangent line is just its rise over its run. That's 50 pounds over a 2 foot change in my height. And if I simplify, I get 25 pounds per foot. Well, we are also asked to interpret this. And remember that because we found the slope of a tangent line, we are finding an instantaneous rate of change. So this 25 pounds per foot, I'll just write it up here since I've run out of room. This 25 pounds per foot, it's the slope of a tangent line, so it's the instantaneous rate of change of your output variable, which is W, your weight, with respect to your input variable, which is no longer time. Your input variable is now h, in other words, with respect to your height. So it's an instantaneous rate of your weight, how much your weight changes compared to your height. So the instantaneous rate of change of your weight with respect to the input variable of height. So it's how fast you're gaining weight as compared to how fast you are growing, as compared to a unit change in your growth. And if you want to, then you can think, well, at that instant in time when you reach 3 feet tall, you are gaining weight at the instantaneous rate of 25 pounds per foot of height change, per unit change in your height. All right, the next thing we're going to do is look at an example where instead of being given a graph of one quantity compared to another input quantity, we're going to look at an example that's more like the pumpkin example we did, where we were given an equation. So let's do that next. So now let's go ahead and look at an example where we're going to find an average rate of change and an instantaneous rate of change, and we're given the equation for the function instead of being given the graph of the function. So let's look at this example. I'm looking at the cost of producing X bicycles. So maybe you have some garage business and you're producing custom bikes for people. I knew somebody who did this, and he actually ended up being quite a famous bike maker. So he's going to make X bicycles, and it costs him a certain amount in materials, in rent, maybe rental of equipment or tools, things like that. So the cost of producing X bicycles is given by this formula. C of X is X squared plus $6,000. Okay, great. Well, in part A here, we want to find the average rate of change of C with respect to X. And you notice in part B, we'll be finding the instantaneous rate of change of C with respect to X. Well, if I want the average rate of change, remember that in terms of the graph, if I were to graph this function with X, the number of bikes I produce along the X-axis, and C, the cost of producing that many bikes along the vertical axis. Well, what would this graph look like? It would be some kind of, I guess it's a parabola. If you draw y equals x squared plus 6,000, it has a y-intercept of 6,000. And then is a parabola that opens upwards from there. I'm not going to graph this very accurately, but it's really only the right half of the parabola, because we don't want to think of X, the number of bicycles we produce, as something that's negative. So for our physical problem, we would want X to be something that's greater than or equal to 0, but not negative. So we get the right half of a parabola. It looks something like this. We want the average rate of change of C with respect to X when we go from producing 100 bikes to 103 bikes. So somewhere along here is 100 bikes, and it corresponds to some cost. And somewhere along here is 103 bikes, and we want the average rate of change of C as we go from producing 100 bikes to 103 bikes. Well, what is that geometrically? Remember, we said the average rate of change of C is going to be equal to the slope of the secant line geometrically. So that would be the secant line that goes through the point corresponding to x equal 100 and the point corresponding to x equal 3. So it would be this secant line, or the slope of that secant line. And how do we find the slope of the secant line? We just do the change in C over the change in x. It's the rise over the run of that green secant line. Well, how do I find that? Remember that the number of bikes is going from 100 to 103. That's my x value, is going from an x value of 100 to x equals 103. So we figure out the cost at the second value, C of 103 costs a certain amount to make 103 bikes, we figure out the cost at x equal 100 costs a certain amount to make 100 bikes, and that will be the change in my cost values as I go from producing 100 bikes to 103 bikes. I divide that by the change in x, the change in the number of bikes that I'm producing. That's going to be 103 minus 100. So we just go ahead, and now because we're given an equation for c of x, I can actually plug 103 into this function and figure out what that cost is. And I believe I did that in my notes. It turns out that if you do 103 squared and add 6,000, you get $16,609. So that's the cost of producing 103 bikes. I subtract the cost of producing 100 bikes. That just means I put 100 in for x, so I do 100 squared and add 6,000. That would end up giving me $16,000. And then I divide by 103 minus 100, that's the number of bikes, so that would be 3 bikes, by the units in the denominator. And let's see, that's going to end up giving me 609 divided by 3. What is that? 609 divided by 3 would be $203, and that would be the number of dollars per one bike. Or another way of writing this would be that it's $203 per bicycle. So it costs me an average of $203 per bike when I go from the level of producing 100 bikes to the level of producing 103 bikes. So that's the average cost of the number of bicycles for that production range, from 100 bikes up to 103 bikes. Well, let's go ahead and see if we can answer part B. In part B, I don't want the average rate of change. I want the instantaneous rate of change of my cost with respect to x when we're producing exactly 100 bikes. So when I'm at that production level, is the way that we usually say it, 100 bike production level, I want to know how fast is my cost changing with respect to the number of bikes that I'm producing. Again, if you think about this graph of x versus c, be the same graph that we talked about before. Here's the y-intercept of 6,000, and I have a parabola that opens upwards from there. And here's my x value of 100 bikes. What am I asking for? If I'm asking for the instantaneous rate that c is changing with respect to x at x equal 100, it means I'm not looking for the secant line, but rather I'm looking for the tangent line slope. So I'm looking for the slope of this blue tangent line to my curve right at the point P that corresponds to x equal 100. Alright, so the instantaneous rate of change of the cost with respect to the number of bikes I'm producing is geometrically the slope of the tangent line. So here's my tangent line. So it's the slope of this blue tangent line. And how do I find the slope of any tangent line? Remember that I want to find the derivative. So I want the slope of the tangent line. That means I'm looking for c prime of x. If I want the instantaneous rate at x equal 100, I would just plug in 100 in place of my x value. And that would give me the instantaneous rate at this particular point on the graph. Well, let's go ahead and find c prime of x for a general value x, and then at the very end we'll plug in x equal to 100, and that'll give us the instantaneous rate of change of the cost with respect to x at the 100 bicycle production level. Well, how do I find c prime of x? Unfortunately, at this point in time, the only way we have to find c prime of x is to do our limiting process. Later, we will learn some shortcut methods for doing this, but right now, to find c prime of x, I have to find the limit as h approaches 0. Normally, we have f of x plus h minus f of x in the numerator, but our function is called c of x, and so I would have c of x plus h minus c of x, all divided by h. And I have to find the limit of that expression as h goes to 0. Well, we have to figure out what c of x plus h and c of x are for this particular function. And keep in mind, I'll just do this on the side here, that c of whatever I plug into this function, whatever my x is, so c of empty parentheses is going to be, and I'm just going to replace all the x's I see on the right, there's only one of them, with a set of empty parentheses. It's going to be whatever I plug into my function squared plus 6,000. So c of whatever I plug in for x is going to be whatever I plug in for x squared plus 6,000. Well, we're going to have to figure out then what this expression is for this particular function, and that means I want to plug into my empty parentheses an x plus h. So over here on the right hand side, c of x plus h on the right would be x plus h, that quantity squared plus 6,000. So when I go to rewriting what this expression is for this particular function, this c of x plus h here becomes exactly what I've written on the right. It is x plus h, that quantity squared, plus 6,000. I'll put some little square brackets around this because it's this whole expression is c of x plus h for this particular function, c of x equals x squared plus 6,000. I'm supposed to subtract off c of x. So what is c of x for my particular function? Well, that's just the given function. C of x is x squared plus 6,000. Be a little bit careful here because we're supposed to subtract all of c of x. So I have to put some kind of parentheses around this. I'm using square brackets here, but you could use rounded parentheses as well. But just be sure to put that in parentheses because you don't want to subtract just the first term of your cost function. You want to subtract the entire cost function, which is x squared plus 6,000. And then, according to my formula for c prime of x, I have to still divide all of that by h. Okay, let me put that in purple. Now, if you were to just go ahead and say, well, let's see if we can do this limit by direct substitution, in other words, replace the h's I see with a 0, you notice that you'd get x plus 0 squared. That would be x squared plus 6,000. But you're also subtracting x squared plus 6,000. The numerator, you can check yourself, is going to be approaching 0. The denominator, as h goes to 0, of course, the denominator is h, so that will go to 0. And what kind of form do we have? Once again, we have an indeterminate form. Well, when we have an indeterminate form for our limit, remember that means we have to rewrite our expression. We can't tell yet what the limit is, but if we rewrite, we may be able to figure that out. Okay, well, just as usual, we do the same kind of steps that we've already talked about. If I want the limit as h goes to 0 of this expression, I have to multiply all of this out. X plus h quantity squared, we've done this kind of thing before, would be x squared plus 2xh plus h squared plus 6,000. That's everything that's in the first set of green brackets. And then remember that this minus sign that's in front of these square parentheses here has to be distributed to each term inside. So what does this become when I distribute this minus sign? It's a minus x squared and a minus 6,000. So just be a little bit careful of that minus sign out in front. And now we have some huge long expression, but you may notice that a bunch of things drop out. I have a positive x squared and a negative x squared. Those add up to 0. I have a 6,000 and a minus 6,000. Those add up to 0. And notice, just as in all the other examples that we've looked at in this section, the terms that are left contain a common factor of h. So I'm going to go ahead and factor out that common factor of h in the numerator, and I would have an h times 2x plus h, and the whole thing is still divided by h. Well, what can I do now to simplify? I have a factor of h in the numerator, a factor of h in the denominator. H over h is just 1 in a special form, so I get to cancel those out, and I am left with the limit as h approaches 0 of 2x plus h. This is a polynomial in h. Remember, the x is unaffected by h going to 0. It's like a constant as far as h is concerned. So the only thing that's going to 0 here is my h, and I would end up with, when I allow h to go to 0, I end up with 2x. That acts like a constant. Limit of a constant is a constant. Plus, and I use direct substitution on h, I get 0 there, so I end up with 2x. Okay, that was a long derivation, but what did we just find? We just found c prime of x is equal to 2x. Now remember, what we really wanted was the instantaneous rate of change of c with respect to x when x equals 100 bikes. So what I really want is not c prime of x, I really want c prime of 100. But I've just gotten a formula for c prime at a general x value, and my formula is c prime of x is 2 times whatever my x is. So c prime of 100 would be 2 times my x value is 100, and I would get c prime of x is 200. So that's the slope of this tangent line at the point corresponding to x equals 100. That's the instantaneous rate of change of the cost with respect to the number of bikes at the 100 bicycle production level. Let's put some units on that. The units are exactly the same as the units that we had for the average rate of change. It's how many dollars per bike. So what we're saying is that it's $200. It's really whatever the output units are, and the output units are in dollars, divided by whatever the input variable is, and the input is the number of bicycles, so it's $200 per bike. Output variables over output variable, or unit I should say, over the input unit. So our instantaneous rate of change of c with respect to x right at this point is $200 per bike. So what that means is that at the 100 bike production level, the cost of producing additional bikes is going up at the rate of $200 per bike. That's as opposed to the average rate of change over a change in production level from 100 bikes to 103 bikes, which is just a bit more, $203 per bike. And I think you can even see, because we know what this curve looks like, it's some kind of parabola that's scooped upwards like this, that this blue line will have a slightly smaller slope than the secant line through the point at 100 and the point at 103. So it makes sense that this slope that we ended up getting of $203 per bike is a little bit larger than the slope we got for the tangent line, which was only $200 per bike. Okay, well, let's summarize everything that we've said so far about the derivative. So on the next page, we're just going to do a general summary at the top of what we've said so far about the derivative. And you may notice that there were really two parts to our discussion of the derivative. We started by just talking about the tangent line to a curve at a point and the slope of that tangent line, and we eventually gave a name to the slope of the tangent line to our curve, y equal f of x, and we called this the derivative of our original function f of x, and we gave it a special notation which we called f prime of x. So that's how we started kind of the whole first part of this topic. Then we went on to talk about velocity, and we expanded on that idea to rates of change of functions in general, the rate of change of any output variable compared to any input variable. Well, this means that we actually have two different interpretations of the derivative. So we have two interpretations of the derivative, which we denote f prime of x for a given function y equal f of x. So here's a nice graph of our function y equal f of x, and the first interpretation is the one that we talked about right here. We can think of f prime of x as being the slope of the tangent line to the graph of our original function y equals f of x. So one interpretation of the derivative, at a particular value x, f prime of x is just the slope of the tangent line. So if this is my x value and here's my point P corresponding to that x value, well, there's some tangent line through the black curve y equal f of x at that point, and whatever the slope of that tangent line is the derivative of my function at that particular x value. So interpretation one is a geometric interpretation. The derivative is the slope of the tangent line to the graph of y equal f of x. We had a second interpretation for the derivative that isn't geometric. Our second interpretation had to do with a rate of change, and we said that f prime of x is the instantaneous rate of change of our output variable, which is y in general, with respect to our input variable, which in general we call x. If we were talking about an s equals f of t curve, a distance equals some function of time curve, it was the instantaneous rate of change of s, the distance or position, with respect to time, which is also called the velocity, the instantaneous velocity. But in this more general setting, f prime of x will be interpreted as the instantaneous rate that y is changing with respect to x. It's the instantaneous rate of change of our output variable with respect to our input variable. And another way of sort of saying this just informally is f prime of x is how fast, it's a measure of how fast our outputs are changing with respect to or per unit change in our inputs. And this is not quite as precise, but a lot of times students like to think about f prime that way. It's a rate of change, means it's saying how fast are the outputs changing per unit change in the inputs. For example, in the last example, part B, we found the instantaneous rate of change of the cost with respect to the number of bikes at the 100 bike production level, and we ended up with, oh, I see, the output, the number of dollars is changing by 200 for each one bicycle that we produce. It was a rate of change of $200 per bike, so the cost is going up by $200 per unit change in the number of bikes we produce, so per bike. Okay, well, that's actually about all that we're going to say about derivatives in terms of instantaneous rates of change, but we will use this idea of the derivative being the instantaneous rate of change over and over again throughout the next few chapters. Every time we hit an application problem, it describes usually some function that has outputs and inputs, and the derivative of that function will be the rate that the outputs are changing with respect to the inputs, and it will always be the instantaneous rate of change of the outputs with respect to the inputs.